this leads to a completely wide open field so far, and it's a huge potential for this particular research area. Then what is biosensor? Biosensors are analytical tools for the analysis of biomaterial samples to gain an understanding of their biocomposition, structure, and function by converting biological responses into an electrical signal. I guess you all are mostly from the background of engineering, so you'll be understanding this more, in detail as we move on. The analytical device is composed of a biological recognition element directly interface to a signal transducer, which together relate the concentration of an analyte or group of related analytes to a measurable response. Components here, if you see the schematic diagram, how it works, the components of biosensor, you first have an analyte. What is analyte? Analyte is a substance of interest that needs detection. For instance, glucose is an analyte in a biosensor designed to detect glucose. Then you have a bioreceptor. Bioreceptor is a molecule that specifically recognizes the analyte and is known as a bioreceptor. So what are these bioreceptors? You can say it is enzymes, it is cells, it is aptamer, it is deoxyribonucleic acid, that is your DNA, and antibodies are some examples of the bioreceptors. The process of signal generation here it depend upon the interaction of the bioreceptor with the analyte. Okay, once these two get interact, then you get a biorecognition. So then we move on to another component which is required for biosensor, that is your transducer here. So these are mostly your electronic terms, and most of you must be aware about it. So transducer is an element that converts one form of energy into another. This converts one form of energy into the another. In a biosensor, in particularly, the role of transducer is to convert the biorecognition event into a measurable signal. So it converts whatever is the bioanalyte, and it will convert into a recognition signal. Okay. So this process of energy conversion is known as signalization, and then most transducer produce either optical or electrical signal that are usually proportional to the amount of analyte or bioreceptor, which forms the interaction between analyte and the bioreceptor. Then you have certain electronics are there, components which is involved. One is amplifier, other is electronic. So this part of the biosensor in terms of electronics possesses this transduced signal and prepare it for a display. Display means your final output. It consists of a complex electronic circuit that performs signal conditioning, such as amplification and conversion of signals from analog into a digital form. So from till here, this is analog, and then it transforms into a digital form, and then it gives a display that is your final output. So what will be the display look like? So display, the final output results will be in the form of the part. The display consists of a user interpretation system, such as the liquid crystal display of a computer, or direct printer that generates number or curves understandable by the user. This part often consists of a combination of a hardware and software. So basically, at the end, you have a PC. Nowadays, you even have a pad connected to it, and you can see the output of your result. The output signal on the display can be a numeric. So if you testing your glucose level, then what you get? You get a simple reading, right? Some numbers you get. If it is in a normal range, then it is between 90 to 110. If it is above normal, then it goes up to 200, 400. And if it is at the insulin level, it is 400 to 500. So these are the numeric value what you get on the display. Then it can be a graph. So if you see ECG machine, you put your sensors all along your body. There are 5 sensors which you put at different location, and then what you see over there is your graph output. Okay, Then it can be a tabular or an image. If you go for a sonography or if you go for a CT scan, then you find as imaging outside there. The output is an image. So depending on the requirements of the end user. So these are the complete components for the ideal biosensor to work. Then we just go for a historical background. The history of biosensor dates very back as early as 1906, when M. Creamer demonstrated that the concentration of an acid in a liquid is proportional to the electrical potential that arises between parts of the fluid located on opposite sides of a glass membrane. So, however, it was only in 1909, you can see in 1909, that the concept of pH, that is hydrogen ion concentration, was introduced by Soren Peder, Loritz and Sorensen, and an electrode for pH measurement was realized in the year 1922 by W.S. Hughes. Between 1909 and between 1922, there is a huge changes was observed. So Griffin and Nelson first demonstrated immobilization of enzymes invertase on aluminum hydroxide and charcoal. The first true biosensor was developed by Leland C. Clark, as we have known, in 1956 for oxygen detection. He is known as the father of the biosensor also, and his invention of the oxygen electrode bear his name, Clark electrode. So these are some historical background for biosensors. Characteristics of biosensor. So we know the components. We have seen the historical background of the sensor. Now coming to the most important part is the characteristics of biosensor. What are the features which actually we needed to find out whether this biosensor is working fine or not, whether this can be a very good biosensor, whether this can be applied industrially at the larger scale, as a startups or anything. So for that, you need to know the few important point, the characteristic of biosensor. The first one is this can this can be optimized by several properties. The first one is selectivity of the biosensor. Selectivity is perhaps the most important feature of a biosensor. Selectivity is the ability of a bioreceptor to detect a specific analyte in a sample containing other admixtures and contaminants. The best example of selectivity is depicted by the interaction of an antigen with antibody. Classically, antibodies act as a bioreceptors and immobilize on the surface of the transducer. A solution containing the antigen is then exposed to the transducer, where antibodies interact only with the antigens. To construct a biosensor, selectivity is the main consideration when choosing the bioreceptors. Okay. Then we have reproducibility, another very important criteria to meet the biosensor. Reproducibility is the ability of the biosensor to generate identical responses for a duplicated or triplicated readings. So for every experiment, not only in biosensors, but if you going for a research purpose, then everybody has to repeat their reactions, their experiments, and make sure it is reproducible, it is repeatable at least for 2 to 3 readings. So then you yourself will get confidence, and then if you are moving ahead for patent, for publication, then these are the most important characteristic, most important viable point is reproducibility. You should have a reproducibility of your result. Then you have a stability. Stability is the degree of susceptibility to the ambient disturbances in and around the biosensing system. So if you have some disturbance, so it should not be destabilized. Your biosensor should not be destabilized. So you need to be careful. You need to find out. So these disturbances can cause a drift in the output signals of a biosensor under measurement. This can cause an error in the measured concentration and can affect the precision and accuracy of the biosensor. Stability is the most crucial feature in applications where a biosensor requires long incubation steps or continuous monitoring. The response of transducer and electronics can be temperature sensitive, which may influence the stability of a biosensor. Therefore, appropriate tuning of electronics is required to ensure a stable response of the sensor. Another factor that can influence the stability is the affinity of the bioreceptor. So the affinity of the bioreceptor, which is the degree to which the analyte binds to the bioreceptor. So that is also one of the factor which can affect the stability. Bioreceptor with the high affinities encourages the bioreceptor with high affinity encourages either the strong electrostatic bonding or a covalent linkage of the analyte that fortifies the stability of a biosensor. And another very important factor that affects the stability of a measurement is the degradation of the bioreceptor over a period of time. So if you made your probe, and if it is not stable and if it is degrading your material to the probe, the material of your probe, if it is not stable and if it is degrading, then it will affect the stability, and that will eventually affect the readings of your biosensor. Then another most important point is sensitivity. Sensitivity is the minimum amount of analyte that can be detected by a biosensor defines its limit of detection. So for any sensor, you need to know the limit of detection. That is up to what limit it is going, whether it is going in the micromolar level, whether it is going in the nanomolar level. So these are the important points which we need to, any biosensor has to take care. In a number of medical and environmental monitoring applications, a biosensor is required to detect analyte concentration as low as nanogram per ml or even sometimes femtogram per ml to confirm the presence of a trace of analytes in a sample. For instance, a prostate specific antigen, that is PSA, concentration of 4 nanogram per ml in blood is associated with the prostate cancer, for which doctor suggests biopsies test. So this is a thing like one, just for example, if you have level of PSA is more in your body in the concentration in the blood, then you go for different testing. So that may lead to some kind of diseases. Okay. Then another important point is linearity. So linearity is the attribute that shows the accuracy of your measured response. So how accurate is your response of your sensor, biosensor? So that is one of the most important part in this. And generally, it has been plotted by a straight line. You plot all your readings against the concentration with your reading or with your voltage with the current reading, but it should have a very straight linear line. So your plot will be say y is equal to mc is your slope, so your slope should be somewhere around 99% or so. Okay, so then it is the perfect linearity, means perfect is your sensitivity, your accuracy of your sensor. Okay. So then we move on to the applications of biosensor. Biosensors are a huge applications available for sensing of different things. Have a very wide range of application that aim to improve the quality of life. This range covers their use for environmental monitoring, disease detection, food safety, defense purpose, drug discovery, and many more. One of the main application of biosensor is the detection of biomolecules that are either indicators of a disease or a target of a drug. So for example, if you have a electrochemical biosensing techniques, then can be used as clinical tools to detect the protein cancer biomarkers. So biosensor can also be used as platform for monitoring food traceability, quality, safety, and nutritional value. So all this thing in the food industry also, it is a very vital tool. Biosensor is a very vital tool. This application fall into the category of a single shot analysis tool, that is where the cost effective and disposable sensing is platform are required for the application. And on the other hand, an application such as pollution monitoring, you see Delhi during this winter, you see how the worse the situation becomes because of, smoke coming from neighboring states and all. So all those can be done by the sensing, by using the biosensors. Uh, and then you have an application such as pollution monitoring, so requires a biosensor to function from a few hours to several days. Such biosensors can be termed as long-term monitoring analysis tools. So this, this smoke, what you see in Delhi, so it remains for at least half of the winter there, and that's why so for to monitor that you need a biosensor which is called as for the long term biosensor monitoring tools. So whether it is long-term monitoring or single-shot analysis, biosensor find their use as technologically advanced device, both in limited settings and also in terms of sophisticated medical setups. Okay, for example, with the application in drug discovery for the detection of number of chemical and biological agents that are considered to be toxic materials of defense interest for use in artificially implantable devices such as pacemakers and other prosthetic devices, and sewage epidemiology. So these are the range of electrochemical, optical, and acoustic sensing techniques have been utilized so far. So biosensor in short is, and as I told you in the beginning of my talk, that everybody right now, especially I think the students who are really, there is not a single student who I can think that, who don't use any gadgets nowadays. So whether it is a smartwatch, whether it is a smartphone, whether it is tab, whether it is iPad or anything. So everything you have it, sensing, there are some biosensor inbuilt in it. You go for a treadmill, you have a biosensor which shows your pulse, which shows your number of steps, everything. So these are all parts of the biosensing tools. Okay. Then types of biosensors, there are different way of detection mode of biosensor. So there are electrochemical, electrical, optical, and mass sensitive thermal biosensors. So these are the different types. So we'll just focus on electrochemical and optical biosensors. So I'll show you some of the examples from our group also what we have published based on these two techniques. So what is electrochemical transducer? Consists of potentiometry or amperometric are most popular based of their familiarity to chemists and biologists as well as simplicity of the operation. It has a added advantage that the same device can be used to sense different types of redox molecules, provided their redox potentials are distinctly different from one another. Then in case of optical biosensor, light is focused on a membrane containing reagents which can combine with target molecules diffusing through the membrane. As a result, reagents can absorb or fluorescence or emit, which is measured, and thereby concentrations of target molecules are determined. And then you have a colorimetric biosensor based on bioanalytical colorimetry test. That is just by looking at the color change, you can see whether this particular analyte is sensing any particular metal ions or any other biological component. So these are the important parts for the electrochemical and optical sensing part. Then electrochemical biosensors, if you see, generally the electrochemical biosensor is based on the reaction of enzymatic catalysis that consumes or generate electrons. Such type of enzymes are named as redox enzymes. The substrate of this biosensors generally includes three electrode system, such as counter So these are the techniques under which in the in the electrochemical sensor, which comes under electrochemical sensor: amperometric biosensor, potentiometric biosensor, impedometric biosensor, and voltammetric biosensor. So we'll be looking at the voltammetric and amperometric and some impedometric biosensors as well. So, but this consists of a three electrode system. Uh, One is a counter electrode, another one is a reference, and the third one is a working electrode. The object analyte is engaged in the response that happens on the surface of an active electrode, and this reaction may source also electron transfer across the dual layer potential, and the current can be calculated as a set potential. So this is how the amperometric biosensors, the functioning of amperometric biosensor is a self-contained incorporated device based on the amount of the current ensuing from the oxidation offering exact quantitative analytical information. Then you have generally these biosensors have reaction times, energetic ranges and sensitivities comparable to the potentiometric biosensors. The simple amperometric biosensor in frequent usage includes the Clark oxygen example. The Clark oxygen electrode is one of the very famous example for amperometric biosensor. The rule of this biosensor is based on the amount of the flow of current. So it is based on the amount of flow of the current. It is based on the amount of the flow of the current between the counter electrode and the working electrode. So you can see in the counter electrode and the working electrode are parallel to each other, close to each other. So it is the role, the flow of the current is between the counter electrode and the working electrode, which encouraged by the redox response at the operational electrode. Choosing analyte centers is essential for a wide selection of uses, like comprising high throughput medicine screening, quality control problem, finding and handling the and biological checking. These are all part of the sensing by the amperometric biosensor. Then in case of potentiometric biosensor, this type of biosensor provides a logarithm. This provide a logarithm reply by means of a high energetic range. These biosensors are frequently complete by monitor producing the electrode prototype lying on a synthetic substrate covered by a performing polymer with some enzymes is connected. They comprise two electrode systems which are enormously responsive and strong. They allow their recognition of analyte on stages before only attainable by the HPLC and LCMS and without exact model preparation. So if you have a very, very pure sample, then this is of use where you can directly use as a potentiometric biosensors. Then in impedometric biosensor, this is also called as electrochemical impedance spectroscopy, is a responsive indicator for a broad range of physical as well as the chemical properties. As you can see in the diagram here, there are antibodies, artificial binding protein, DNA, and RNA aptamer are involved. A rising trend towards the expansion of impedometric biosensor is being presently the observed. The technique of impedometry have been executed to differentiate the invention of a biosensor as well as to examine the catalyzed responses of enzymatic lectins, nucleic acid receptors, whole cells, and antibodies, etc. Okay, so this is used to examine the catalyzed response of enzymes. Then piezoelectric biosensor, this will be of use to you in conditions of classification. Physical biosensors are the most fundamental as well as broadly used sensors. The main ideas behind this categorization also happen from inspecting the human minds, as the general working method behind the intelligence of hearing, sight, touch is to react on the exterior physical stimuli. Therefore, any detection device that offers reaction to the physical, possessions of a medium was named as a physical biosensor. So maybe we can take an example of your smartphone, the touch devices where you can touch and you can just slide your finger and you can see what the changes in your, in your smartphone, etc. The physical biosensors are classified into two types, namely the piezoelectric biosensors and thermoelectric biosensors. So the piezoelectric biosensors, these sensors are a collection of analytical devices which works on a law of affinity. Interactions recording, as I told you, it is based on the interaction. The platform of a piezoelectric is a sensor element works on the law of oscillations transform due to a collection jump on the surface of a piezoelectric crystal. Okay, so this is the piezoelectric biosensors. Then thermoelectric biosensors, there are various types of biological reaction which are connected with the inventions of heat, and this makes base of the thermometric biosensor. These sensors are usually named as thermal biosensor. Thermal means heat is involved. So whenever there is a heat is involved and there is change of some biological component, then this can be used as a thermometric biosensors are of potential use. This is used to measure or estimate the serum cholesterol. A cholesterol obtains oxidized through the enzymes cholesterol oxidase. Then the heat will be produced, which can be calculated. So similarly, assessment of glucose, urea, uric acid, and penicillin G can be done with this type of biosensors. Okay. Then you have an optical biosensor. This is also very important and it's the most commonly used biosensor, the optical biosensor. It's a device that uses an optical measurement principle. They use the fiber optics as well as the optoelectronics transducers. The term optrode represents a compression of the two terms, optical and electrode. These sensors mainly involve antibodies and enzymes like the transducing elements. Optical biosensor permit a secure, non-electrical, accessible sensing of equipment. An extra benefit is that this frequently do not need reference sensors. Okay, this doesn't need two sensing two electrode system or three electrode system. It does in under one simple box of either it could be a spectrophotometer or it could be a fluorimeter, etc. An extra benefit is okay, you do not need any reference sensors because the comparative signal can be produced by using the similar light source like the sampling sensor. The optical biosensor are classified into two types, namely direct optical detection biosensor and labeled optical detection biosensors. So this is one such example which I was talking about you from beginning, that now we have everything in our hand, all the biosensors. So these are some of the variable biosensors you can see. You have a position sensors, you have a airflow sensor for breathing, you have a electrocardiogram sensor ECG for the which shows you the graph of your heartbeats, and you have a different health component for measuring your oxygen level. You have a oximeter, etc. You have a wide variety of sensors it's available. So the wearable biosensor is a digital device used to wear on a human body in different wearable systems like smartwatches, smart shirts, tattoos, which allows the level of blood glucose, BP, the rate of heartbeat, etc. to know just on your device on your hand. You need not even go to doctor also for checking your BP, etc. Nowadays, we can notice that these sensors are carrying out a signal of improvement to the world. Their better use and ease can give an original level of experience into the patients and real-time fitness status. This data accessibility will let superior clinical choice and will effect in enhance health results and extra capable use of health system. So nowadays, even your doctor will come to know if there is some, if you have an increase in heartbeat, if you have an increase in BP. So your doctor is sitting maybe in another country or in another city somewhere, but he'll come to know, "Oh, okay, my patient is suffering from high BP," so he will immediately text him, "Okay, right now your BP is very high, so you please," he may prescribe some medicine as well, that you please start taking this medicine, etc. So these are the advancement in the biosensors from the overall biosensors, the advancement what I mean we have seen across. We started from 1905 and now we are in 2020. We see how the world has changed and everything is on your tip of your finger, that you want to know your heartbeat, you want to know your pulse, you want to know your sugar level, you want to know your BP, everything you yourself can see, and even your doctor sitting wherever in the remote, very far away from you, but he is on having a record of yours, every every disease, everything. So that's the progress we have made in biosensor. Having given you this background of biosensors, now I'll take you the next half. I'll take you to my, the life work, what we have actually, what we have made, what kind of probe we have made, and what we have, sense in our group as a part of our research work. Okay. So this will be more exciting for you all to study and to see how we are practicing this biosensor in our laboratory as a research. And okay. So we'll start with our first project, development of fluorescence turn-on probe for aluminum-3 sensing. Why aluminum-3? Because, in our neurological system or in our body, there is some contents of particular amount of aluminum which is required, and at the same time, if you have a excess amount of aluminum in our body, then that leads to a severe disease. So one such very common disease, if I name, is Alzheimer. If the content of your aluminum is increased in your body, you see many old age problem. The maximum old age problem now also it's the Alzheimer. uh, People lost their memory, they forget, they keep forgetting, then they remember, then they forget. So these are the things. This is one of the most crucial element, plays very vital role in your biological system of your human physiological system. So sensing of aluminum is really very essential in that point of view. So we started our work. What we did, one of my student, Dr. Anup. So this was, I think, our first or second work in our group for sensing, optical sensing. So he has prepared, he has taken some very simple molecule. So, yeah. So what we have taken a mesitylene group, which is having two amino group at their respective meta position, and this group, this amine was reacted with naphthaldehyde, which is having one of the hydroxy group on the ortho position. So this was simply reflux for 4 hours in methanol. And what we could find is we could find this particular product, which was characterized by various means like NMR, IR, and then finally we also able to could get the we could able to authenticate by single crystal X-ray studies. So this structure, what you see, this is the part of single crystal X-ray diffraction. So we could able to generate a single crystal of this L1 molecule, and we could able to characterize. So the first step was to do the reaction, get your product, and just characterize your product, whether your product is formed or not. So yes, we characterize it, and then we found that this is 100% what we wanted. The product has formed. Then we looked at the photophysical properties. So in photophysical properties, what do you see? You see UV, by using UV visible spectrophotometer, you see the absorption behavior of this particular ligand. So that's what we did. We have done the UV. So the plot A shows the UV absorption titration spectra of L1 versus aluminum metal ion. So what we did, we have done the titration of L1 with aluminum metal ion, and the condition was the concentration of aluminum metal ion was 1 into 10 to minus 5 molar in aqueous acetonitrile and acetonitrile water mixture. And what we found that with the increase in the addition of aluminum ion concentrated solution, you can see there is a you can see this particular peak is started decreasing, and here you can find a new peak which is coming up at 360 nanometer and followed by 419 nanometer. And this actually leads to one new isobastic point. It is encircled at 391 nanometer, which suggests that it is a new isobastic point, a particular absorbance at which no change observed during the chemical reaction. The appearance of the isobastic point during the titration results indication of very strong interaction between your host and the analyte. Okay. Then what we did, we thought to see competitive studies with whether it is only specific to aluminum ion or whether it can actually sense any other metal ion as well. So what we did is we have taken our ligand and we started adding other metal ions. So you can see with other metal ion there was no change was observed. So when we added aluminum, then you can see a very prominent change in the UV spectra was observed here. That means that our probe, that is our ligand L1, is very specific to aluminum 3 metal ion. Then after having a UV visible studies, that is absorbance studies, we thought to check whether it is showing any fluorescence behavior. So what we found is, if you see the graph 1, with increase in concentration of aluminum metal ion, you can see the increase in the fluorescence intensity was observed, and which was very linear. As I told you, you remember I told you that linearity is one of the most important part in the development of any biosensor. So we could able to get a very highly linear curve here with reference to the concentration, with reference to the fluorescence increase in the enhancement in the fluorescence intensity, that is 99.25. So we can say this is a very good sensor in terms of linearity. You can see that it is a very good sensor. Then again, we thought to check in presence of other metal ion whether it is specific to aluminum or it can also be fluorescence with any other metal ion also. So we did this test, and what we found that with other metal ion there was not much increase in there was the fluorescence intensity remains constant. But as soon as you add aluminum metal ion, you can see about 8-fold increase was observed in the fluorescence intensity. So that suggests that our metal ion, our ligand L1 is highly specific and sensing aluminum 3 plus metal ion. Having said that, another point what I told you is the selectivity of a chemosensor. So with the selectivity, we have tried this in presence of 23 different metal ions. And what we found that if you see the plot 1 here, A1, so here you can see but this is very specific with aluminum only. So the fluorescence intensity turn on only with the aluminum metal ion. And similarly, we did with different other metal ions, and that is the effect of influence of other metal ions in the presence of aluminum already is there. Then you add another metal ion, that itself shows that it is specific to aluminum only. Okay, then after saying that, we also did the colorimetric detection of aluminum 3 using L1, and you can see in this all these different metal ion, You can see that only when you add aluminum ion, it is showing a different in color, which suggests that it is highly colorimetrically also it is specific to aluminum 3 plus metal ion. We published this in Nature Scientific Report journal in 2016. Then we also thought to see the emission spectra and fluorescence response time, what is the lifetime of this particular sensor, etc. Lifetime, when I say, it's like, the response time, what is the maximum response time we can wait for. So in the A, you can see it is also tunable at different wavelength with different color combination with a shift from blue to green region at different wavelength. At 405 it is blue emission is observed, at 488 it is green emission, so it is highly fluorescent in nature. We also did a DNA binding test, and we saw that, yeah, when you add aluminum to the ligand and in presence of DNA, you can see a very prominent high fluorescence intensity was observed. The fluorescence response time for this particular sensor was 120 seconds. That is quite appreciable response time in terms of the sensing of aluminum. So another important aspect for any sensor is the reversibility of chemosensor, whether it is reversible in nature or not. Because if it is not reversible, then it is no point of having a sensor for us. So it should be reversible. Of course, it should be turned on and off. So we did this example by using a simple EDTA. You have the purple line, the pink line. What you see here is your ligand fluorescence. When you add aluminum plus and then when you add aluminum ion, you see it is increasing at eightfold increase is observed. Enhancement in fluorescent intensity is observed as soon as you add aluminum. Then when you add EDTA, you see again it is going off. It is coming down. The fluorescent intensity is immediately coming down. And then when you again put aluminum excess, then again it is going back. So if you see this particular one, if you put aluminum, the fluorescence is increasing tremendously. And when you add EDTA, it is again diminishing. The fluorescence is diminishing. So this suggests that your chemosensor is L1 is your highly is very specific to aluminum, and it is a very good sensor because it is also having a reversibility nature. So after having this, then we thought that what about checking this particular whether this this sensor is toxic or non-toxic in nature. So there is a study called cell viability, which you do it, and what you see is at up to 100 micromolar concentration of your L1 and by adding one that is your aluminum that one second. So this is your L1. When I say L1 is my probe ligand only, and when I say one is after adding aluminum, when it binds, when this ligand bind to aluminum, so it becomes one. So both are highly fluorescent in nature. In fact, one is more fluorescent in nature compared to L1, because after we add aluminum, your fluorescence sensor is enhancing up to 8-fold, so highly fluorescent in nature. So in that way, we have recorded the cell viability. That means up to 100 micromolar, you can see 80%, more than 80% of the cell was still alive. So to find out the toxicity of any molecule, any compound, any material, the minimum requirement is up to 50 micromolar. If your cell is 50% of your cell is still alive, that means your compound, your molecule, your material is highly cell viable, that is non-toxic in nature. So in our case, it was far superior than what is the required form. So what we see is that this is non-toxic in nature, so we can use this for our cell line studies in biological systems inside your body. For different cell lines, we can use it and we can see it. So having this excellent photophysical properties, we thought to go ahead and see what is whether this aluminum is whether this probe is sensing aluminum inside the cell lines. So that was the most challenging part for us to find out the cell line studies and inside the cell line studies. So what we did is we started with prostate cancer cell line, that is DU145. And here are the images. If you can see here, when Du-145 in the at 405, so it was so L1, along with its low toxicity, it was employed as an intracellular aluminum 3 plus sensor using confocal laser scanning microscopy. So Du-145 cell lines and breast cancer cell lines, MCF7, were first treated with 10 micromolar of ligand and incubated for 45 minutes at 37 degrees Celsius. The L1 treated cells was subjected to confocal microscopy and was excited using lasers having wavelength of 405 and 488 nanometer. As depicted in the figure, you can see here the treatment with L1 resulted in a very weak intercellular fluorescence with blue and green color. These are very weak. There are some fluorescence, but very weak fluorescence it observed in blue and green region. A signal at a different excitation. Further, after adding 10 micromolar of aluminum 3 plus was added to these cells, and a considerable enhancement in dual both the color. You see, as soon as we added aluminum here, you can see there is a tremendous glow in the fluorescence is observed in case of 405, that is blue, as well as 488, that is in green region. So, and you can see the overlay of both highly extremely fluorescent nature was observed in both the cases. Okay. So here you can see this is the thing. So that means that yeah, our aluminum metal ions is highly sensible inside the cell lines also. If you treat the cell line with ligand, there is a very weak fluorescent intensity is observed. But as soon as you add an aluminum metal ion to it, you see the fluorescence is glowing so tremendously. It is enhanced, the fluorescence intensity enhanced again multiple times. So, and very evident that intracellular multicolor imaging potential of one. Same thing we did with the different cell line, MCF cell line, that is breast cancer cell line, and same thing observed when you add aluminum to a ligand, then the fluorescent intensity increases several fold and becomes highly fluorescent in nature once we see this. So what we conclude is we report a specific and sensitive intracellular sensing of aluminum 3 plus ion by 1, and which is prepared in a very facile and simple manner. Okay. So moving on to another, biological biosensor, what we have made in our group was is a highly selective and sensitive chemosensor for L-tryptophan by employing a Schiff-based copper complex. So here we have prepared a series of Schiff-based metal complexes. We use copper. We have used the same L1 ligand here. When we treated that ligand with different metal ions, in case of copper, it is forming a mononuclear copper complex. In case of nickel, it is forming a similar type of mononuclear copper complex, where 1:2. One part is the metal ion, other two part is your ligand ion. And when we treat it with zinc in the similar fashion, monomeric form is formed, and with the cobalt also. So with all the four metal ions, PCS monomeric copper metal complexes was formed. But among these, what we did is copper complex was found to be highly, potentially very good probe for sensing L-tryptophan. We did a photophysical properties of a copper complex here, and you can see the AVV's, UVV's absorption titration spectra of one with tryptophan. So here you can see we did the same thing. Here you can see there is 4 different isoblastic point was observed, which means that the connection with copper complex with L-tryptophan is potentially very strong. Similarly, we did the same things, selectivity with different metal ions. So in different amino acids we took, because tryptophan is one of the amino acids. So we use similar different amino acid, and what we found is that this copper complex is highly selective to tryptophan in nature. As soon as you add tryptophan, You can see the different, a completely different UV-Vis spectra was observed. So that shows that one is selective towards tryptophan. Then the same thing what we did, we have done, first we have confirmed, or first we have analyzed, or we have detected the formation, the sensing of L-tryptophan by optical sensing method, that is fluorescence and UV. Then what we did, we went to electrochemical sensing by using cyclic voltammetry. We have observed whether it is can be detected through electrode system also, and to our surprise, yes, it was sensing L-tryptophan. The same copper complex was sensing L-tryptophan through electrochemical sensing also. So here, what we took 3 electrode system. So our working electrode was a glassy carbon electrode. Okay, so what we did, we have coated this material of copper complex onto the tip of the glassy carbon electrode, and we left it overnight for drying. And then when we started our experiment next day, we observed that this particular electrode was quite stable to carry forward the reactions, to carry forward the experiments of sensing. So here you can see a separate different colored coding lines, very colorful. So your black color, if you see the black color at the back, this is the black color cyclic voltammogram. So black color cyclic voltammogram is your bare electrode. So without without coating with our copper complex, you can see that, and just sensing and then just using L-tryptophan in the solution, we took directly blank bare GC electrode. So this is the cyclic voltammogram which was found, the black one, the very thin, the very thinnest cycle. Hello. Yeah, so the black one is the bare electrode, where you see no potential, not much potential is observed. Then the red one is your bare GC in presence of L-tryptophan. So there was not much changes in also. Then what we did, we prepared a glassy electrode by coating our copper complex. So that is your blue color, where they have seen the, in absence of just with the phosphate buffer, you can see slight enhancement in the current year. The cyclic voltammogram over here is slightly increased, but when you add L-tryptophan to this phosphate buffer, and when you use this modified glassy electrode with our copper complex, you can see so much increase, that is about 3 to 4 times enhancement in the current is observed by applying certain potential to the electrochemical setup. So we applied a certain potential, and what we found is this particular electrode is sensing L-tryptophan very specifically through electrochemical sensing also. Then what is required here is again the same thing, that you need to check whether this particular electrode is stable or not. So for that we did a scan rate from 10 millivolt per second to 300 millivolt per second, and we found that it is found to be very quite linear in nature with this particular all the different scan rate. Then we have seen the C type is for a different concentration of L-tryptophan. So we introduced 5 to 50 micromolar concentration, and we checked at every different interval of concentration. There was a linear increase in current was observed, and you can see the linearity is also very good here, even 98%. So it is with respect to scan rate, with respect to concentration, in both the cases, our electrode is performing very linearly. So it is highly linear. So it is highly specific electrochemical sensing for L-tryptophan. So here we conclude the sensing behavior of one towards L-tryptophan was confirmed by UV titration as well as cyclic voltammetry measurement. To the best of our knowledge, this is the first report where L-tryptophan oxidizes at such a very low oxidation potential, that is at 0.32 volt. This was the first report we published on this. which proves the remarkable electrocatalytic activity of one towards the one means copper complex towards the L-tryptophan. Then we move on to another materials. So far we have seen ligand as a sensor, we have seen complex as a sensor. Now what we did is we are moving to a new chemistry, that is MOF, that is metal organic framework, and it is combination, and its combination with graphene oxide. So what we did, we have prepared and that particular combination or that particular composite can be used for sensing of cholesterol. So here what we did, we have prepared a copper MOF. You can see MOF means it's a metal organic framework, and which is having a porosity in nature, which is also having a huge, surface area is also quite good for MOF. And MOFs are used in very different types of application. For that, I need a different talk or different lecture to give you about the MOF, how it works, what is the application. That's a completely entirely different research area, metal organic framework. So what we did, we prepared a copper MOF by using copper as a metal ion, and there was a then you have a linkers. So we have used one of the linker which can create this copper MOF. But for what we use for this particular sensing ion purpose is we use the copper MOF along with the graphene oxide. We made a composite of it by ultrasonication in ethanol, and what we found is the composite of copper MOF with graphene oxide composite. And this was characterized by powder XRD. You can see a very strong peak at 225 2 theta, which corresponds to the graphene oxide peak. And what you can see is the single crystal, the MOF, copper MOF, and the difference between the copper MOF powder XRD as well as the powder XRD of the copper MOF with GEO. So apart from all the peaks, there are some extra peaks at 25 which can be seen for the GEO group. Then to check the morphology, we did SAM analysis, that is scanning electron microscopy, which shows this. The B1 is your copper MOF. This block shape block shape material is our copper MOF morphology, and A is our graphene oxide moiety. So when we combine this, you can see this particular completely composite of copper MOF and GEO is found in this D. So this is your copper MOF crystals, and this hazy cloudy shape is like a graphene oxide composite material. So you can see the composite has well formed during the synthesis purpose of ultrasonication. So having this in our hand, we decided to go for sensing of it. We use the electrochemical sensing method here. So you see the black color peak here is your bare electrode. When you use bare electrode, serial profile of copper MOF for GEO is in the red, and in absence of cholesterol, you can see this is black in color. But as soon as you add a cholesterol to this modified electrode, you can see a complete enhancement peak in red color is displayed here, which shows that quite an enhancement in the current is observed. So this means that our copper MOF graphene oxide composite is sensing cholesterol very strongly. Then we saw the effect of concentration. You can see how effect of concentration plays very important role. You can see a very distinct linearity is observed in case of oxidation peak. And you can see so this is your oxidation peak. Here your cholesterol is getting oxidized, and then it is coming back and reducing the cholesterol. So it is a reversible process. And for both, you can see for oxidation reduction peak, the calibration plot is very linear in nature. And we went up to the limit of 0.0 millimolar concentration to be limit of detection, what can be, what we can actually sense, or what we can actually analyze up to the limit of 0.09 millimolar. So the conclusion, we made a new copper MOF composite. Graphene oxide composite was synthesized by simple ultrasonication method. Then the incorporation of graphene oxide into the metal organic framers has improved the properties of the synthesized composite material through synergistic effect. Then copper MOF Geo was explored for selective electrochemical sensing of cholesterol. The first report on hybrid material prepared from metal organic frame and graphene oxide for electrochemical sensing of cholesterol. So this is the first example you can see. So now what we saw is your ligand as a sensor, we saw metal complex as a sensor, then we move to another stage where this is copper MOF, a completely huge structure of copper, you can say copper complex, a complete huge structure which is in the MOF form. Metal organic framework is a three-dimensional structure, three-dimensional, very complex topology. And then after doing this, I'll take you to some examples where we can do optical biosensors using nanomaterials. So we move on to a pure nanomaterials and see how the sensing is taking place. So these are some reported material, what you can see, the sensing was done. Is it, so do I have some time?
Yes, sir, you can carry on.
Okay. So the irrespective of the field, miniaturization has always proved to be beneficial for varied reasons. For instance, reducing the size of the biosensor to the micro or nano scale can result in a better signal to noise ratio, as well as the possibility of using smaller sample volumes, which means lower assay cost. Moreover, when going towards the nanoscale dimensions, the surface to volume ratio of the sensing active area increases and the sizes of the detection electrode and that of the target biomarker becomes comparable. Okay, so keeping all this in mind, we move to looking into the nanomaterials level and see whether this can give a very good sensing response or not for different properties. So our first work in this was to prepare a copper oxide and graphene nanosphere composite as colorimetric dual sensor for hydrogen peroxide as well as cholesterol. So here we could able to get sensing of two analytes, the hydrogen peroxide and cholesterol. Uh, needless to say that both of the components are very important for your human physiological system. Okay. So how did we do it? We took a graphite powder. We have added some. This was done by Dr. Vinay. Now he's in UCLA. We added some sulfuric acid and nitric acid ratio mixture, ultrasonicated for 3 hours, and then further we heated for 90 degrees Celsius at 90 degrees Celsius for 90 minutes. What we found is the graphene nanosphere was prepared. The nanoparticle of graphene nanosphere was prepared, and this graphene nanosphere was used further to combine with copper oxide, and their composite was taken, ultrasonicated and heated to give the graphene oxide GNS system, that is your graphene nanosphere. So we found graphene nanosphere, and so then further when so this can also be done directly when you add everything together. That also is possible. You can find copper oxide and then you ultrasonicate with graphene nanosphere and you find the copper oxide graphene nanosphere composite. So we have characterized this, and you can see A is the powder XRD pattern for the first one is for graphene nanosphere. You can see at 25 very strong peak of graphene is observed. Graphene oxide is observed at 25 2 theta. Then followed by copper oxide peak, which is comparable with the reported copper oxide in the JSPDS system. Then we see the blue color plot. If you can see, that is for the combined of the composite of copper oxide as well as GNS. So you can see the both red and black peak all combined together in the blue peak, which is the composite of copper oxide and GNS. Then FTIR also suggests the same thing. Formation of this composite is very well formed. Then you have a TAM below that. The C consists of TAM. TAM is very clear. You have a copper oxide. Then you have a graphene nanosphere is very well visible in the TAM, and that is the morphology. TAM is transmission electron microscopy, which is actually used at nanometer level to see the morphology of your nanomaterials. Then you have a UV. You have in UV also it is quite clear that all three are having a specific absorption peak, and the profile of TGA to check the thermal stability of this particular compound. So having this, we have seen how the sensitivity detection of H2O and is observed. So you can see the H2O2 detection is done when a phenol is treated with H2O2. It forms this particular moiety, and by using peroxidase or yeah, the copper oxide or the copper oxide GNS composite, the analyte, the sensing material, you can actually see the absorbance changes in with increase in the concentration of H2O2 here. And similarly, in linear correlation, in concentration, you can see concentration of H2O2 and absorbance is highly linear in nature. So this means that our probe is working very well for detection of H2O2, and thus LOD, that is limit of detection, was found for H2O2 sensing was found to be 6.8 micromolar. Okay, so during this process, what happens is you find the cholesterol threon when your cholesterol is reacted with oxygen of which is released from the H2O2, and this can be sensed through our composite CuGNS by so once you react this with oxygen, what you get it cholesterol en threon, and also there is a sub unit called H2O2 which is coming out. So here you can see the coming out H2O2 as a byproduct can also be sensed by our product, by our probe copper oxide GNS composite. You can see this is colorless, and as soon as you treat with our composite, it is transforming into orange color. So that can be detected as well. So it can be simultaneously detect, it can dual detect both your cholesterol as well as H2O2. Okay. So this is the cholesterol sensing. You can see absorbance change with increase in concentration of cholesterol. A very linear correlation between the concentration of cholesterol and absorbance is found here at very highly linear in nature. The LOD, that is limit of detection for cholesterol sensing, was found to be 78 micromolar. So overall, what we can conclude is we report a facile synthesis of cytocompatible peroxidase mimic copper oxide graphene nanosphere, which are composite, and it can be colorimetrically sense dual can work as a dual sensor for hydrogen peroxide and cholesterol sensing. Then after saying this, we move to another very important nanoparticle, which we made it. That is a multicolor fluorescent carbon nanoparticle probes for dual palladium and mercury sensing. As I told you in beginning, so in West Bengal and other places where the lakes are very much polluted, the rivers are very much polluted. So if you see a huge amount of heavy metals like mercury, lead, and palladium kind of thing. So for that, sensing is very important. So we use this particular material, our carbon nanoparticle, as a probe for dual palladium and mercury sensing. So what we did here is we use a citric acid and ethylene diamine at 250 degrees Celsius at 5 hours, and what we found is this leads to formation of carbon nanoparticle. And when you excite at 340 nanometer, it gives the very highly fluorescent nature of and it is a multicolor fluorescent is observed at 440 nanometer. So it react it or it gives dual sensing. It gives palladium 2 plus sensing, and it is also leads to mercury 2 plus sensing. This was characterized by various means, powder XRD, SAM of carbon nanoparticle. You can see a very small, tiny spherical form, and then it is confirmed by photoluminescence, spectra, FTIR, etc. So this carbon nanoparticle was formed, which is characterized by various means. Palladium and mercury sensing, so you can see that fluorescence quenching of CNP in presence of noble metal palladium and mercury is observed here. Here quenching is taking place. The carbon nanoparticle itself is highly fluorescent in nature. Okay, so the sensing is done through quenching. So once you add palladium or you add mercury, your your fluorescent nature actually start quenching. So it goes from highly fluorescent in nature to diminish the fluorescent intensity. So, so here you can see it is this black color is your fluorescent carbon nanoparticle, but as soon as you start adding mercury to it, it start diminishing. Similarly, if you add palladium, it start diminishing. But in both the cases, linearity is observed. That means your sensor is very accurate in nature. So after having a very good photophysical properties and very strong fluorescent in nature, we again thought to check whether we can actually detect mercury inside the cell line. So as per our plan, we can see that when you add your carbon nanoparticles is highly fluorescent in nature, but after adding control with mercury 2 plus ion, with over time you can see that fluorescent intensity started decreasing. That means that when it is reacting with mercury, it is the fluorescent intensity is decreasing. That means it is sensing mercury inside the intercellular sensing also. So it can be used for intercellular sensing purpose of mercury ions. Suppose if you have a content of mercury consumed through the fishes and all through food or something, then you can actually sense the intracellular sensing can be done. So here I would like to conclude by saying that carbon-based nanomaterials are emerging as a desirable alternative to semiconducting quantum dots due to their unique optical properties and biocompatibility. Detection of palladium 2 plus mercury 2 plus by a ton of mode using citric acid based carbon dots. Real sample analysis and intracellular detection has also also being carried out for the sensing purpose. Then we move to now earlier we use citric acid as a source for making a biosensor for making a carbon dots. But what we did, we further move on and we tried to use a greener source to make the carbon dots so that there should not be more any any kind of toxicity level comes from any place. So what we use here was green carbon dot as a as an optical biosensor. So here what we did, we use a various source used for the synthesis of carbon dots. So we started with sugarcane. We use a sugarcane, actual sugarcane or the pulp of sugarcane, and we reduce that to a carbon dot. Then one of my student Vinay, just after Valentine Day, he came out with a lot of roses. So I asked him like, what are you going to do with these roses? So then he only suggested, shall we prepare a carbon dot of it? I said, yeah, go ahead. And so he actually used those roses for preparing a carbon dot, and that works as a wonder for us. Then further we used Vigna radita sprouts, the daily sprouts what we use, and we reduced that to carbon dot. And then we use cannabis sativa also, and we prepared a carbon dot for this, and all this actually gives a wonder for us. So with this, what we could able to sense was With sugarcane, actually, we could able to sense various pH. It worked as a pH sensor. The carbon dot prepares through sugarcane actually worked as a uh, actually it worked as a pH sensor. Then when we use rose petal carbon dot from rose petal, it worked for detecting or for sensing sulfide and the gold
Carry on.
sulfide and a gold sensing was done. Then with Vigna radita sprout, the carbon dot prepared through Vigna radita, we could able to sense Fe3 plus ions. And with cannabis, we could able to sense vitamin B12 ion. So this all was done by using photophysical properties, optoelectronic sensing properties. So here you can see the pH sensing is done using the nitrogen and phosphorus doped functionalized carbon material. That is what we have used by sugarcane. So here you can see it is sensing the various range of pH over here. In the range of 9 to 14 fluorescence lifetime decay, and the reversibility in sensing is observed over here. And you can see the stability up to 5 cycle. It was highly stable in nature. The sensing response for NS-RCT, that is by using the rose petal, we have made this particular fluorescence, this particular sensor, carbon dots, which is used for sensing sulfide ion, with sulfide ion as a on turn on sensor. So when you have a carbon dot, which is still very fluorescence in nature, when you have sulfide, it is turning on, it is going on increasing the fluorescence intensity. But as soon as you add gold to it, it is start diminishing the fluorescence. So it was both turn on and turn off was observed in this particular case as a sensor. So in both the cases, we could able to sense the intracellular sensing of both was also possible for sulfur as well as for gold was observed. The sensing inside the cell lines was done. Then we have this Vigna ratida. We have used this sprout as a carbon material source, and here we could able to sense Fe3 plus ion very easily. With increase in concentration of Fe3 plus ion, you can see a linear plot was observed. So the sensing of iron is done very accurately. There was no issue in this. Similarly, intracellular sensing was done of iron by using this particular carbon dot. We use confocal of HeLa cell treated with in a nitrogen doped Vigna radita carbon dot, and we could able to very easily sense Fe3 plus ion inside the cell lines also. We use HeLa cell lines for this particular work. Then finally, by using cannabis sativa, we could able to sense vitamin B12 inside the cell lines, and also photophysically, you can see the UV and all with increase. And this was a turn off sensor was observed. So in conclusion, heteroatom doped rosa indica, that is your rose based carbon dot, rose petal based carbon dots was developed for interesting turn off on off mode with sulfide and gold metal ion. Then excellent reversibility in selective pH dependency makes heteroatom doped nitrogen phosphorus functionalized carbon material we have seen. Then cannabis sativa based sensing of vitamin B12 was observed, and then sensing of Fe3 plus ion was observed by using the Vigna radita sprout. So I think so this is the basic principles of electrochemical biosensor, which I just wanted to show you how it is done. And so you have a substrate on the surface electrode, and then the surface electrode surface is first coated with the enzymes, and then you have a substrate. And when you actually apply voltage, you see the product formation, and the major current prop up to the concentration of the substrate. So we did the last studies which I want to show you is that the glucose detection was done by using nickel cobalt oxide nanorods as a sensitive enzyme glucose detection. So here we prepared, the nickel cobalt mixture composite of nanorods, and which was used further for detection of the glucose sensing purpose. So in the first case, you can see with the bare electrode, there was hardly any current response was there. But as soon as you introduce your modified electrode and you sense the glucose, you can see a quite increase in the area inside the cyclic voltammogram. That means your electrode is ready for sensing of glucose as a sensor. So we applied different strategy here. This is through cyclic voltammogram, this is through amperometric, and these are the things what the uh, sensitivity and interference studies was done by using amperometric detection. And then further, we have also able to get glucose studies done by another material, that is copper oxide nanosphere also. So here we use the screen printed electrode instead of glassy carbon electrode. Here we have made a copper oxide nanosphere was prepared. You can see this particular moiety. These are carbon copper oxide nanosphere, which was used as a modifier for the electrode to find the actually to find the glucose. Okay. So again, we did the same. CV was done. You see the pink color is quite enhanced surface, quite enhanced area was observed under the cyclic voltammogram, which suggests highly specific nature of sensing of glucose by using this particular copper oxide nanosphere as the modifier for the electrode. And this was the sensitivity, and LOD was recorded up to 20.6 micromolar with response time less than 5 seconds. So commercially available blood glucose strips, you can see how it works. It works on the electrochemical analysis, electrochemical studies only. By using 3 electrode system, you have a working electrode, you have a counter electrode, and you have a reference electrode over here. So cross section of the commercial strip for self-testing of blood glucose. You can see the A is your electrode system, and B is your hydrophobic layer drawing the blood. So this is the basic setup, and this when you insert in any of your glucometer. So the biggest reason that designs change is that somebody realized that there could be a better way to get the same job done. So going back to the blood glucose testing above, the clinic test system was much better than urine testing. So but it is still wasn't the best. So urine glucose testing wasn't the most accurate measure of blood sugar, and the process was still fairly messy. So in that case, they have come out with this strip where you just give your drop of your blood, and you could able to sense the your glucose level in your blood. Okay. Then just for a brief stuff, I can tell you what is the market analysis here for the global biosensor market by product. So if you want to go for a startup, there's a huge demand for wearable biosensors is increasing. You see, from if you start from last 2 years, the use of wearable biosensor in 2026 will be 50% compared to non-wearable biosensor. So it's a huge market, uh, is wide open for the youngsters like you to take up biosensors as a platform to launch your product. Okay. Then in summary, just wanted to say biosensors are nowadays ubiquitous in different areas of healthcare. Pregnancy tests, glucose monitoring sensors are the two main examples of very successful biosensor devices. A range of transduction techniques such as electrochemical, optical, and acoustic can be used for biosensor. High affinity reagents such as antibodies, enzymes, and synthetic biomolecule can be coupled to the transducer in order of to provide the specificity of the biosensor, and nanotechnology has made a major impact on recent advances of the biosensing technology. Most importantly, now we have seen some introduction of AI, artificial intelligence, and IoT also has been introduced in this biosensing purpose. So there's a wide open area. The way you think, you can design your biosensor. And finally, in our work, what we have seen, we started with ligand. We have done some metal complexes. We have shown the example of MOFs and their composite. Then moving into nanomaterial. In nanomaterial, we have used the green source of nanomaterial also. So all this combined was used as a sensor for the complete biosensing platform. Yeah, so these were the part of complete biosensors what we use. Then finally, there is a challenges in biosensing research. So you need to follow certain ethics associated with the use of the developed biosensor, etc. Stability, cost, and ease of the manufacturing each component of the biosensor. So these are the very minute detailing of the biosensor, and then this is the biosensor market again. So biosensor technology is becoming a game changer in recent times. Finally, I would like to acknowledge my institute, IIT Indore, CSIR and SERP for funding, Sophisticated Instrumentation Center, IIT Indore for various characterization techniques and other characterization facility across the globe. So this is my group, a very rare picture where all my research scholars are smiling. So this is one of the most rarest picture you will see, that you will find only in my group. All the research scholars are happy and smiling. And finally, thank you all for your long wait and patience. So I'm open for any question answers.
Good afternoon, sir.
Yeah.
I have some questions.
Yes.
When we talk about metal organic framework, there are a lot of controversial points and research about that.
Yes.
How do we determine the proper dimensions or parameters for making metal organic frameworks for sensors?
You mean to make and so yeah, so in that case you need to be working, you need to be focused on your for metal organic framework consists of two part. One is your metal nodes, that is your metal center, and the other part is your spacer ligand. So you need to design your ligand in such a way so that your porosity of your metal organic framework, which is the final metal organic framework what you get. So your porosity should be, in accordance with the sensing what is there in your mind, what you want to sense. And also the functionality, the functional group which direct inside those porosities. Suppose if you have an amine group which is directing inside the porosity, so the amine group has two hydrogen ions. So how strongly that can bind to, maybe if it is a cholesterol or if it is some enzymes or other thing or any medicine purpose, drug delivery purpose. So those things we need to keep in mind while designing the MOF.
Yes, sir. So basically, the functionality is the first
Yeah, yeah,
thing,
and the
and then the
porosity also. Porosity also.
yes, sir. So another question is, when we use fluorescence for detecting the or sensing the aluminum or copper ions,
Mm-hmm.
sometimes we might use it in practical applications like Alzheimer's, as you said. When
Mm-hmm.
we use biofluids,
Mm-hmm.
amino acids tend to give noise in the fluorescence at different times based on their concentration and other compositions in biofluids. How can we overcome this problem?
You see, what we are talking at very low level of concentration. So I don't think the noise will be so much for that. We talk about in whatever we do it in a micro liter of sensing. Like you use a very micro gram of aluminum in particular ml concentration. So it can be reduced in that way. You need to work in a very smaller concentration, so there won't be much interference of amino acids, so the peak and noise to peak ratio will be completely diminished at particular.
Okay, sir. So, about the same sensor, I have another question too. In the ligand part, while detecting, I mean, when we do a literature survey for identifying some prospective ligands or so, or looking up to what kinds of parameters we have to look for a ligand, we stumble upon a lot of different structures. How do we filter? Like, do we use any computational studies for studying the interaction between them?
No, no. So what you need to see is while making your ligand, you need to see the how much conjugation it has. The more the conjugation, more good fluorescence response will be there for the ligand. And at the same time, you need to see if there are certain, certain bonds which are not suitable for particular pH, and also those things we have to take care of it. The most important part is the conjugation. The more the conjugation, better will be the fluorescence response. So it will be highly fluorescent. So if once you have a ligand which is highly fluorescent in nature, then you can really play around with a lot of sensing performance.
So, ligand designing in essence is up to strict rules in stereochemistry.
Yeah, stereochemistry also there, but what I would suggest is your conjugation of double bond, single bond, as much you can store it in that. That will give you a better uh, ligand performance in terms of optoelectronic properties.
Okay, sir. So, my final question is in today's, especially in today's news,
Mhm.
the hot topic about microbots was from Cornell University. It
Uh-huh.
was about a microbot which can be used for drug designing or targeting a particular molecule like cancer cell.
Mhm.
We can use a microbot, we can inject it into a blood and then make it go to a cancer cell and then deliver the drug. In such kind of an therapeutic advances, what kind of regulatory framework do we have at the moment? Because technology can be used in either ways.
So I tell you, you're giving example of Cornell. So US has a very strong regulatory to go to the market. Suppose they want to take it to the market, they have several very strong stages. Of course we also have it, but very few turns up to the market level. But in US, because of US having a very strong collaboration between industry and academia, so there the norms are also very stringent norms are there, and but it is well placed.
Yes, sir. Thank you, sir.
Okay. So any other questions from student side?
Hello, sir. Good afternoon.
Yeah, good afternoon.
I am Satyavak. Actually, I have some
Hello.
question. So, sir, first question is you told about a lot of biosensor technology.
Mhm.
So, my question is which biosensor technology will be in most demand in user nearest future,
If
and
you
what?
talk very immediate, if you talk about immediate requirement, is of course testing COVID. So that is also a part of sensing only. So having said that, yeah, so these are the general is like, so with your lifestyle, you just think the way we are having our lifestyle, the common diseases is still the challenge is about your, this sugar that is diabetic. You have a problem with cholesterol, these two, and cancer of course is the most, if we can develop something to detect cancer at the earlier stage. So these three will always remain the priority for all of us.
Yes, sir. Got it, sir. So, my next question is on which basis means the parameters you consider during the doing in the determining the performance of biosensors.
Can you repeat please? I could not hear the.
Sir, means I want to ask that how you determine the nano biosensors performance means on which parameters you consider to determine the performance of biosensors.
So in the beginning, I told you there are several parameters like sensitivity, selectivity, and suppose if you're going talking about your nano materials, nanoparticles, then of course the most important part is it has to be non-toxic inside the cell. So non-toxicity is also a very important parameter that your sensing material should not be toxic in nature. Otherwise, the whole purpose will lose. Selectivity, stability. So these are the things which are important.
Sir, a question on that selectivity, sir. How you target to a particular molecule, particular biomolecule, or where there is a similar type of molecules are there, but you target to
Yeah,
a
so
particular biomolecule,
this you will
right?
reach only after reading certain, the references and literature work, because now we have a ample of literature for every molecule what you want to sense. So you know that if you design something, this particular moiety, if you have some design molecule, so you know that what is reported with this similar design molecule. So you can just check the literature and reach out to your, the target sensor.
Yes, sir. Sir, inside the body, some microchips are there we use, and how these chips are powered.
Yes, so as we just now, madam has given you example of microbot. It can go through your so these are made of material which is non-toxic in nature that can stay inside your body, and this can be controlled through nowadays everything is possible. You have a AI. You fix a certain small IC which can gives you the signal from anywhere in India, from anywhere in the world, that what is going on inside your body. So these are the things now it is very much possible. So in fact, you are you in the engineering background?
Yes, I am from computer science background, sir.
Oh yeah, wow. So I mean, you have to tell us. We are just a scientist. You have to tell us, okay, sir, let's do this way.
Yes, sir. But
You,
that can
you
be,
have a
sir.
knowledge about AI. You have a knowledge about IoT. So you have to tell me, sir, let's prepare this thing, and you make this, and I will give you the signaling process. I can
Yes,
take
sir.
care.
When it comes to energy, means we can also wirelessly we can power up some device. That
Yes,
is possible nowadays. Yes, sir.
exactly.
But in general, if you see, sir, is there any mechanism so that we can power up the microchip by using our natural body temperature?
There is a scope for that. There is a scope. See, when you touch your thumb and all, because maybe you can just use your fingerprint itself, because nobody in the world has the same fingerprints. So every human being has a different fingerprint. So you can use your fingerprint as well as a sensor to turn off and turn on your microchip.
Yes, sir. Yes, sir. Got it, sir. Thank you, sir.
So yeah, so, I mean, I'll be glad to hold any of you when the things become normal to come and spend some time in our lab, and we'll be open for your, very young minds, young ideas, how we can convert our sensors to at the next level in the cheap form or in the
Yes, sir.
marketable form.
Sir, how you see the integration of computer science in this biosensor technology? What is the opportunity? How much we
Oh,
can include CS technology in the biosensor? Because nowadays we are seeing that computer science or IT is everywhere.
exactly,
Right?
exactly, exactly. Computer science has a huge scope, I tell you. It's a huge scope. But the problem with computer science, to be honest, you guys only look for very nice software companies, etc. So sorry to say that. But if you really look into the literature, I mean, I can tell you that it's a huge scope in sensing and biosensor, etc. We can do wonders if you join hand with chemists or scientists, computer science and scientists. We can really do a wonder.
Yes, sir. So we think that now we have a great opportunity to use this platform to use our computer science knowledge in this biosensor technology, because in future we are going to or this in this platform we will
Future
use,
is
sir.
AI and IoT.
Yes, sir. AI and IoT.
So this is controlled by you guys only,
Yes, sir. Thank you, sir. Thank you, sir.
right? Hello, hello, hello.
Uh,
Yeah. Am I audible?
yes, sir, you are
Yes, sir.
audible.
Yes, sir. You are audible, sir.
Yeah. So the future is in your hand. Everything is IoT, and whether it is AI. So you people have to decide.
Yes, sir.
Yes. So any other questions?
Hello, sir. Good afternoon.
Yeah, Mira.
So my question is, you already said that glucose is inaccurately measured from urine sampling, and it is
Mhm.
better. It has a better accuracy in the
Blood.
blood sampling,
Yeah.
even one drop of blood sample, right?
Yeah.
So what is the reason behind this, sir?
I don't know. I'm not a biologist, but what I feel is that it also depends on what time your collection of urine. Suppose if it is early morning, then it may be different, and because the enzymes present in blood and this has to do a lot. But the recent, even there is a recent development that not even blood is required for glucose sensing. Even your saliva can speak out. They can give you the accuracy of the sugar level in your body, blood. So even saliva is also used. I have read some sensor which is detecting blood glucose level by using the saliva also. So it is this. Uh, I really can't answer this because it requires some biological. I'm a chemist and material chemist, so but to me it's like maybe some enzymes which is there in the blood which is more uh, you know are more to which is more responsible for the detection of glucose level in the blood, maybe missing in the urine. So actually yeah.
Thank you, sir.
Hello, sir. Sir, I just want to know that if for COVID treatment, is there any progress for, on this biosensor technology? We can use this for COVID
People are
treatment, sir.
working. People are working. There I know a group in France. Actually, they are our collaborator only. So they are working for that. They are working for that. Still, it's
Okay,
too
sir.
early to comment on that.
Okay, sir.
Okay. So any more questions?
Um, okay, sir. So probably I think there is no more question from the students.
Okay. Okay.
So thank you, sir. Thanks a lot for such an
Okay.
informative
Thanks a
and
lot and stay safe, all of you. Take care. It's pleasure giving this talk in front of all of you.
okay, sir. Thank you, sir. Thanks a
Okay.
lot.
Okay. So I'll just quit, huh?
Yeah, sure, sure.
Okay. Thanks a lot. Bye.